In these problems, we're going to be looking at power series and trying to find essentially a radius of convergence and then an interval of convergence. So first question, we're going to have this series summation n equals 0 to infinity, negative 1 to the n over n squared times x to the n. So we want to find the radius of convergence. So what that means is we want to find, well, essentially kind of start building the interval of convergence, which would be which x's we can plug in, what we can plug in for x, and get this series to be a convergent series. So to do that, I'm going to look at my series and decide which test would I use to show if this is convergent. I'm going to choose the ratio test here. So a lot of times we have x to the n. If you do a ratio test, you'll get an x to the n plus 1 over x to the n, which will give you an x, and then you get some inequality in an x here. So a lot of times ratio works. Sometimes you'll have root, but that would work typically if the sort of part without the x, the negative 1 to the n over n squared, if you could take a nth root of the absolute value there. I'm worried about an nth root of n squared, so I'm not going to use the root test. I'm going to try a ratio test. So I'm going to do a ratio test here. What I've got is here an, well, really I care for ratio test, the absolute value of an, that's going to drop the negative 1 to the n. It's going to be x to the n over n squared, but it's actually absolute value x over n squared. And so what I'm going to do is I'm going to do an plus 1 over an, really absolute value. So I'm going to get, let's see, when I plug in n plus 1 for n, I'm going to get absolute value x to the n plus 1 over n plus 1 squared. That part's the an plus 1. And then the an is absolute value x to the n over n squared. So I need to simplify this, and the ratio test, I basically want the limit of this expression, whole big expression, the fraction, as n, limit as n goes to infinity to be less than 1. Here's what I need. So I'm going to get, let's see, I'll get an n squared over n plus 1 squared. My bottom of the bottom becomes a top, times an absolute value x to the n plus 1 over absolute value x to the n. And let's see, I'm just going to leave the n squared over n plus 1 squared alone, and then absolute value x to the n plus 1 over absolute value x to the n gives me an absolute value x here. So n plus 1 minus n is just 1. It's x, absolute value x to the 1. Okay, so I get that. And then what I'm going to think about here is really I'm going to take a limit as n goes to infinity of the absolute value of the ratio of consecutive sort of terms of our series here. So that's a limit as n goes to infinity of n squared over n plus 1 squared times absolute value x. N squared over n plus 1 squared, that's a rational function. Top and bottom are degree 2, so I'm going to divide their leading coefficients. They're both 1. So n squared over n plus 1 squared will go to 1. Absolute value x has no n, so it's just absolute value x. So here what I get is this ratio is absolute value x. And what I need for the ratio test to get me convergence, actually I will get absolute convergence, if this ratio is less than 1. So essentially here, what I get, is less than 1. So let me just recap here. So our series, n equals 0 to infinity, negative 1 to the n over n squared x to the n, what the ratio test tells us, let's just get rid of this less than 1 for now, is this series is absolutely convergent if this limit as the ratio of the an's is less than 1. So this is absolutely convergent for absolute value x less than 1. Ratio test also tells us that this series is divergent for if we get a result that's absolute value x bigger than 1. So what we get here is essentially we have a setup where we know here on our number line, let's just draw a number line here. So we have x, that's really 0. Absolute value x equals 1, that's x is either 1 or negative 1. What we have here is that in this red area, that's absolute value x less than 1, we know that our series is convergent. Actually, our series is absolutely convergent. And then let's maybe draw a green area, absolute value x greater than 1. So this is x greater than 1, I guess x less than negative 1, that's the two parts of absolute value x less than 1, we know that our series is divergent here. And this is sort of the picture you're going to get for essentially every power series, at least if you interpret certain things a certain way, like the radius of infinity here. But what you get here is you have this sort of center point 0 because x is x minus 0, and it will converge here for things going out a distance of some distance to the right and some distance to the left from there. And that distance is the radius of convergence here. So that distance is 1 minus 0 is 1. So our radius of convergence here is 1. So that's really our radius of convergence here. So that's 1. Now, the interval of convergence is really the other thing we want. Essentially tells us where does this series converge. So it looks like we have that in our picture already, but what we're missing is does the series converge at -1 or 1 exactly. So you could use the ratio test to do this, but if you use the ratio test, you're going to get absolute value x. You're going to get a 1 from this limit that you use for the ratio test, and the ratio test just says that's inconclusive. So we're going to have to do something different at x equals 1, x equals -1. So right now our possible intervals of convergence, here let me just write this up, I don't know, maybe in red here. So we have possible intervals of convergence here. You could get, so these all can happen for various series, you could get really -1 less than x less than 1. So both 1 and -1, if you plug those in, the series diverges. Or you could get -1 less than equal to x less than 1. So the series converges at -1, diverges at 1. You get -1 less than x less than equal to 1. Or you could get -1 less than equal to x less than equal to 1. So really part B here, we know our answer is one of these four things. Basically, do you throw in -1 or not? Do you throw in 1 or not? And the goal is to figure out which of these four is actually the interval of convergence here. So essentially figure out if our power series converges at 1 and -1, and maybe write down that I understand what the radius of convergence means here, that I get an interval like -1 less than x less than 1, possibly with the endpoints thrown in. Okay, so let's attack this. So if x equals 1, our series was -1 to the n over n squared x to the n. Well, I get 1 to the n, so I just get a sum n equals 0 to infinity, -1 to the n over n squared. Now this, I run into a problem here because I can't plug in n equals 0. So I probably have an issue from the start, actually. Just noticed it now. Yeah, this problem doesn't actually make sense because I'm dividing by 0. Let's change this to a 1 here as we go along. So let's just change those to 1s. Won't affect convergence here. Sort of a sloppiness, I guess, on my part here. So we'll get a 1 there. So what I'm going to say here is now this series, this is just a straight up alternating series here. So this is alternating, and we have three things to check here. So it's alternating. I have an equals 1 over n squared. So an's go to 0 as n goes to infinity. So that's true. So our an, as n gets big, our an's go to 0. We need to make sure our an's are greater than or equal to 0. That's true. And we need to make sure if we increase sort of our subscript, we go an plus 1. That's not bigger than an. Wrong way. Should be getting smaller. And that's true too. You put a bigger denominator, you get a smaller fraction. So that tells us that this converges. So that tells us that our original series, so we get our power series converges for x equals 1 here. And what that tells us about our intervals of convergence here is that, well, we have to get a less than or equal to with 1. So this first interval is not correct. The second interval is not correct. Now, let's try x equals -1. So I'm going to get a sum n equals now 1 to infinity, -1 to the n over n squared, and then when you plug a -1 in for x, you get -1 to the n. But -1 to the n times -1 to the n, well, what's that? I get -1 to the 2n over n squared, which is summation n equals 1 to infinity. That's like negative 1 to an even power, that's going to give us a positive 1. So you get a 1 over n squared. Here. So this, I don't have the alternating series anymore, but this is a p series here, so this converges, and that's because it's a p series with p equal to 2, which is bigger than 1 here. So that converges as well, so we actually get convergence at negative 1 as well here. So our answer, cross out this, is really our interval of convergence is negative 1 less than equal to x less than equal to 1. So we got both endpoints. It's going to be convergent. Here. Next one. So here's the same setup. We have negative 1 to the n over 2 to the n x to the n. So this one, I mentioned this in the first question here, where a lot of times I'll do ratio test, unless I can take an nth root here, which is going to work out just fine. So what I'm going to do is I'm going to do a root test. You could do a ratio test as well here. I just want to show the root test. So what I do is I take an nth root of really the absolute value an. That absolute value an is going to get rid of the negative 1 to the n. So this is an nth root of really x to the n, absolute value x to the n, over 2 to the n. And that, after you take the nth root, is going to give you absolute value x less than 2. And so I need absolute value x over 2. Really, I want that to be less than 1 for convergent, greater than 1 for divergent. So what I get here, really, if that was less than 1, let's just solve this. You get absolute value x less than 2. So I center at 0 here because it's x minus 0. And then I'm going to go out to 2 and negative 2. And what I'm going to get is sort of my root test says I'm absolutely convergent in this interval from negative 2 to 2, not including the endpoints. It might be at the endpoints. We have to check those separately. And that if I do something outside here, I'm divergent. So here's divergent, divergent, and here's, it's actually absolutely convergent on this interval, and then there's a question at negative 2 and 2 precisely. So we've got almost everything in terms of almost every value of x, for which, well, for almost every value of x, we've determined if this series will converge or diverge here, just not for x equals 2 and negative 2. We're going to do those sort of separately. And so here our radius of convergence is really just the 2, distance from 0 to 2. So it's a distance from the 0. Okay, so we got a radius of convergence of 2. And now the interval of convergence here, again, we want to check our sets here. Really, we want to check, does our sort of series converge at 2 or negative 2? So we're going to get an interval from negative 2 to 2, possibly adding the endpoints. So what we need to check is x equals 2. Our series, now this one we can do n equals 0 to infinity, is negative 1 to the n over 2 to the n times 1 to the n. Well, 1 to the n is just 1, so this is n equals 0 to infinity, negative 1 to the n over 2 to the n. This one, I mean, I could converge by alternating series test here. I could actually use a root test here as well. If I do this, oh, sorry, except I messed this up here. I said x equals 2, so let's not use a root test here. This series would converge by the root test, but something was bothering me that it seemed like it'd be a little bit easier. I made a mistake here. I plugged in 1 because that was the last time, but I really should be doing x equals 2, so this should be times 2 to the n here. So what happens is the 2 to the n's cancel. I get a negative 1 to the n. And then what happens if you add up negative 1 to the n? Well, that's 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus blah, blah, blah. Your partial sums, here, let's write our partial sums. So this is like our SNs. Here, they're going to go 1, 0, 1, 0, 1, 0, and so forth. It's just going to alternate between 1 and 0. That's not converging. So really, our power series diverges for x equals 2. So we don't get the right endpoint of the interval. What about x equals negative 2? Well, if I do summation n equals 0 to infinity, I get negative 1 to the n over 2 to the n times negative 2 to the n. Well, this is going to be sum n equals 0 to infinity, negative 1 to the n over 2 to the n. Negative 2 to the n I can write as a negative 1 to the n times 2 to the n. Whoops, didn't really need the parentheses there. Suppose they weren't hurting anything. And then you can cancel the 2 to the n's, and you get a negative 1 to the n times negative 1 to the n. That's negative 1 to the 2n, which is just going to give us sum n equals 0 to infinity of just 1. And that's going to be 1. Well, 1 is going to go to, the sum of the 1's is going to go to infinity, and so this diverges as well. So our power series diverges for x equals negative 2. And that tells me that my interval of convergence is negative 2 less than x less than 2. So we included neither one of the endpoints here. Next one. All right, so we do negative 1 to the n, summation n equals 0 to infinity, negative 1 to the n over n factorial times x to the n. So when I see factorials here, typically if these are going to work out nicely, it's going to be a ratio test. So the ratio is probably the nicest thing to do with factorials. There's other things you can do, but this is generally what we should expect. So I'm going to do an absolute value of an plus 1 over an. So the an is this whole thing here. Now when you take the absolute value, the negative 1 to the n basically goes to 1, sort of goes away. So when I do an plus 1 absolute value, I'm going to get absolute value x to the n plus 1 over n plus 1 factorial, all over absolute value x to the n over n factorial. And then I sort of invert the bottom and multiply. That gives me an n factorial over n plus 1 factorial times, let's see, it's absolute value x to the n plus 1 over absolute value x to the n. N factorial over n plus 1 factorial is 1 over n plus 1. Absolute value x to the n plus 1 over absolute value x to the n gives me an absolute value x over 1. So I get absolute value x over n plus 1. A bit sloppy there. And then we do limit n goes to infinity, really of this ratio. Well, that's a limit as n goes to infinity, absolute value x over n plus 1. Now, this is, we're going to fix an x. You plug in any x at all, x is fixed, this n plus 1 in the denominator is going to go to infinity. So I'm going to get some finite number, some fixed number over infinity. That's going to equal 0. Note, that's less than 1. And this tells us something really nice here, that no matter what x we plug in into our original power series here, that we're going to get actually absolute convergence here. So what we get here is that our series n equals 0 to infinity, negative 1 to the n over n factorial x to the n. Let's see, this converges. Here it's actually absolutely convergent for all x here. So that's a really nice thing to say. And now we want to actually, we're asked for a radius of convergence. Here, well, what do we do here? If you draw sort of your number line, here you're centered at 0, and we had sort of those red things. Well, the red region sort of convergence is the whole number line. So we can kind of think of this as going out to infinity here, and so our radius of convergence is actually infinity here. So it's kind of a notation to say, hey, this converges for all values of x. And then similarly, interval of convergence. This one's a little bit nicer because you don't have to worry about the endpoints because there are no endpoints here. Interval of convergence, you could write, let's see, negative infinity to infinity, or you could write something like all real numbers, or whatever version of this you want to have. Maybe you could just write it, so, whoops, sort of r, whatever you want to do here. So it's all real numbers. Okay, next one. This is like, I think it was number 1. Again, I shouldn't be starting at n equals 0. I should be starting at n equals 1 here. I don't want to divide by 0. There will not affect whether the series converges for any particular x at all. I guess unless you think that the series not defined is not convergent, but we're not going to go that route. Okay, so here, what I've got is very similar to the first question, where we had essentially, instead of x minus 2 to the n, we had x to the n. So this is going to work out very much the same way. I'm going to do a ratio test here. and I'm going to do an absolute value an plus 1 over an. So the absolute values, again, essentially get rid of the negative 1 to the n's. So I do an plus 1, I'm going to get absolute value x minus 2 to the n plus 1 over n plus 1 squared, all over absolute value x minus 2 to the n over n squared. And then when I sort of invert and multiply the bottom, I get n squared over n plus 1 squared times absolute value x minus 2 to the n plus 1 over absolute value x minus 2 to the n. This is going to give me an n squared over n plus 1 squared times absolute value x. So I don't worry about simplifying the n squared over n plus 1 squared because I'm looking at this right now and thinking as the limit of this sort of fraction, the n squared over n plus 1 squared, limit of that as n goes to infinity, it's going to be 1. So I got the limit. I don't need to really worry about it. And I'm going to actually execute my limit. Limit of the ratio of an plus 1 to an, the absolute value of that, is the limit as n goes to infinity of n squared over n plus 1 squared times absolute value x. So n squared over n plus 1 squared, again, rational functions, degree of top equals degree of bottom, divide the coefficients, they're both 1s, that gives me a 1. Oh, except it's not times absolute value x. So I made a mistake back here. I wrote absolute value x. Here, this is actually absolute value x minus 2. So absolute value x minus 2. So I get a 1 times absolute value x minus 2. So I get an absolute value x minus 2. Now, what's that mean in terms of our convergence here? Well, I need absolute value x minus 2 to be less than 1. That is, I need the distance between x and 2 to be less than 1. So we get at 2, let's see, if we add 1, you go to 3. If you subtract 1, you go to 1. And so our ratio test gets us absolute convergence between 1 and 3. Also, if we get beyond 3, we're going to get divergent here. So we'll get divergent, and we'll get absolutely convergent. Here. Okay, so this means essentially our radius of convergence here's, well, the distance from our center, which is 2, to the outside. So 2 to 3 is 1, 2 to 1 is 1. So radius of convergence is 1. Now the interval of convergence is going to be 1 to 3, except maybe it includes 1, maybe it includes 3. So when we do the interval of convergence, we have to worry about x equals 1. Well, then the sum n equals 1 to infinity. We have negative 1 to the n over n squared. And then we add an x minus 2 to the n. That's 1 minus 2 to the n. So that's summation n equals 1 to infinity. Negative 1 to the n over n squared. 1 minus 2 is negative 1. Negative 1 to the n times negative 1 to the n. So negative 1 to the n is either 1 or negative 1. You square that, you'll always get a positive 1. So this is summation n equals 1 to infinity, 1 over n squared. This is convergent here because it's a p series with p equal 2, which is bigger than 1. So we get 1, we're going to include the left endpoint of our potential interval. And then when x equals 3, what you get is a summation n equals 1 to infinity, negative 1 to the n over n squared, 3 minus 2 to the n. Well, 3 minus 2 is 1 here. So we get a negative 1 to the n over n squared times 1 to the n. But 1 to the n is just 1. So you end up with n equals 1 to infinity, negative 1 to the n over n squared. Now, this one, I think before I did an alternating series test, we had this actual series, I think in problem 1 here. This one, what I can do is I can take the absolute value. So what I've got here is that the absolute value of negative 1 to the n over n squared is 1 over n squared. And if we put a 1 over n squared in place of the negative 1 to the n to the n squared, we get this series from sort of x equals 1 here, and we know that's convergent. So what that tells us here is that this series is actually absolutely convergent. Here, not just convergent. And we can just use the result before. And what that means is our radius of convergence, we got convergence at x equals 1 and x equals 3. And so our interval of convergence well, we're going from 1 to 3. Next one. Okay, so again, matching it very similar to a previous question. We're going to find our radius of convergence. We have -1 to the n over 2 to the n times x minus 1 to the n. Again, I can use a root test. It's probably simpler if every part, simpler than ratio here, if every part of sort of your an is something to the nth power. So what I'm going to get is the nth root of the absolute value a of n, and that gives me an nth root of, okay, absolute value -1 to the n is just 1 because it's the absolute value. Let's see, so we'll get an x minus 1, actually not just x minus 1, but absolute value x minus 1 to the n over 2 to the n. Take the nth root, and you get an x minus 1 over 2. Now note, the key thing here is we're going to get convergence or divergence from the root test, depending on the relationship between x minus 1 over 2 and 1. So I'm just going to put a less than 1 for convergence. That gets me absolute value x minus 1 less than 2. And so what we get, sort of the picture we've been drawing here. I could take a limit, I guess, as n goes to infinity of this, but there's no n's, so I don't really need to do that here. What I'm going to do is I'm centered at 1 here because it's x minus 1, and it says I can go at a distance of 2. So that's 3 to the right, -1 to the left here. So I get really convergence, actually absolutely convergent on this interval. So it's not just convergent, it's absolutely convergent. And then I get divergence sort of on these endpoints here. Divergent here. Okay, and so our radius of convergence, if all you need is the radius of convergence, that's typically easier here, because our radius of convergence, well, that's the distance from 1 to 3, which is 2, or 1 to -1, which is 2. Those should match. Note, it's the 2 you got up here. You didn't really need the picture here. That's more for interval of convergence, but maybe helps understand what's going on. So that's the radius of convergence, just 2. Interval of convergence, I have to worry, does this original series converge if I throw in a -1 for n or a 3 for n? Sorry, -1 for x or a 3 for x. So let's do x equals -1. Our series is n equals 0 to infinity, -1 to the n over 2 to the n times -1 minus 1 to the n. So just this -1 here, that's where x was. We just put -1 where the x was. So we do a summation, n equals 0 to infinity. I have -1 to the n over 2 to the n times -1 minus 1 is a -2 to the n. And then I can split up that -2 to the n as a -1 to the n times 2 to the n. And that gives me summation n equals 0 to infinity. The -1 to the n times -1 to the n will multiply for a 1. 2 to the n on bottom, 2 to the n on top cancel. I get a summation of 1. That really just goes to infinity, which means my series diverges. So we get divergent for x equals -1. And then the other endpoint was x equals 3. So we get n equals 0 to infinity, -1 to the n over 2 to the n times 3 minus 1 to the n. So summation n equals 0 to infinity, -1 to the n over 2 to the n. 3 minus 1 is 2 to the n. The 2 to the n's cancel. We get n equals 0 to infinity, -1 to the n. And again, that's just going to alternate between 1, 0, 1, 0, 1, 0. And so we get divergent series for x equals 3. And what we get then is our interval of convergence does not include either of the endpoints. So it's just -1 less than x less than 3. So there's our interval of convergence. Next one here, we've got essentially the same thing as number 3, but now we have an x plus 3 to the n instead of an x to the n. Again, I see a factorial, makes me think ratio test is probably the way to go. So I'm going to do a ratio test. And what I'm going to get here is, let's see, a to the n plus 1 over a n, but I have to take the absolute value. This is going to be, let's see, a n plus 1. Let's Let's do the absolute value in each part. So I'll get a absolute value x plus 3 to the n plus 1 over n plus 1 factorial over, if I plug in n, I get x plus 3 to the n over n factorial. So this gives me an n factorial over n plus 1 factorial times x plus 3 absolute value x plus 3 to the n plus 1 for absolute value x plus 3 to the n. And this is going to give me, let's see, I'll get an absolute value x plus 3 on top from the x plus 3 to the n plus 1 over x plus 3 to the n. N factorial over n plus 1 factorial is going to leave me with n plus 1. So I do a limit as n goes to infinity of my ratio. That's a limit as n goes to infinity of absolute value x plus 3 over n plus 1. Again, no matter what x is, x plus 3 is some finite number. So if you fix x and then let n go to infinity, you're going to get a finite number over infinity. This is going to go to 0, which is less than 1. So essentially, this power series will converge for every possible value of x here. And that tells me that my radius of convergence is infinity here. Okay, and then the interval of convergence, given the radius of convergence is infinity, I'm just going to write it as negative infinity to infinity. There, so there's really no endpoints to check. Okay, last question. This is not really a power series question, but it's getting you a sense as to where these series we've been using, these power series, where they come from here. So I guess they don't have to come from these places, but a lot of them are Taylor series here. That is, they're trying to represent a particular function here. So we do a Taylor series at x equals 0 for f of x is square root 1 minus x. So our general Taylor series, what it's going to look like is summation n equals 0 to infinity. It's going to be so f and then n in parentheses. That's the nth derivative of f. We're going to evaluate that at our center point. That's 0 here. We're going to divide by, there's always an n factorial, and then we multiply by an x to the n. So really, x minus 0 to the n is x to the n. So this is a Taylor series centered at 0. It's actually called also a Maclaurin series. You can, maybe the general form, let's write the general form up here, is summation n equals 0 to infinity f, the nth derivative, evaluated at a over n factorial, and then you do an x minus a to the n. So if you centered at not x equals 0, but x equals 1, you put a 1 and a 1, where a is. So here we've got a 0, and then x minus 0 is just x. All right, so to do this formula of writing the Taylor series, not difficult, except you've got to find a formula for the nth derivative evaluated at 0. So the 0th derivative is just f of x. Let's do f of x is square root 1 minus x. And then we'll do, let's see, f of 0. So this is really the 0th derivative. Here, if I plug in 0, I get square root of 1, that's 1. And then the first derivative, here we'll put it in parentheses sort of up in our exponent on the f, tends to mean derivative. We do a derivative of this. So this is 1 minus x to the 1/2. So it's 1/2 times 1 minus x to the negative 1/2. And then by the chain rule, to multiply by the derivative of the inside, which is negative 1 here. So let's just rewrite that as negative 1/2 1 minus x to the negative 1/2. So the first derivative, if you evaluate this at 0, 1 minus x, that's 1, I get a negative 1/2. Okay. Second derivative of x, I get my negative 1/2, and then I'm going to multiply by another negative 1/2, and that's 1 minus x to the negative 3/2, but then I pick up a negative 1 because of the chain rule doing the derivative of 1 minus x. So this works out to be a negative, a positive, a negative of 1 over, I'm going to write it as 2 squared. I could do 4 here, but generally not simplifying these will allow you to see a pattern more easily. Not always the case, but sometimes that's really true. And so I do my second derivative, 0. The 1 minus 0 is just 1 to any power is 1. So this is negative 1/4. Let's do a third derivative. So we get a negative 1 over 2 squared. 1 minus x, sorry, and then I bring down my exponent, which is a negative 3 halves, and then I get a 1 minus x to the negative 5 halves, and then what I'm going to get is times a negative 1 because the derivative of 1 minus x is negative 1. Again, I get 3 negatives, so I'm always going to get this same setup. I'm going to get now 3 over 2 cubed. 1 minus x to the 5 halves. And so the third derivative, evaluated at 0, is, let's see, 3 over 8, so negative 3/8 here. Okay, let's maybe do one more here and then talk about the pattern here. Fourth derivative of x, I get a negative 3 over 2 cubed times our exponent. Whoops, there was a negative 5 halves up there. Exponent is negative 5 halves times 1 minus x to the subtract 1 is negative 7 halves times the derivative of 1 minus x is negative 1. 1, 2, 3 negatives gives me a negative. I have a 3 times 5 over 2 to the 4th. 1 minus x to the negative 7 halves. And then I do a fourth derivative evaluated at 0. Essentially, that's going to be a negative 3 times 5 over 2 to the 4th here. This one is negative 3 over 2 cubed. This one is negative 1 over 2 squared here. First one is negative 1 over 2 to the first here. So if you look at this, what's going to happen the next time? I'm going to multiply by 7 halves here. And if you kind of can extrapolate this out here, your nth derivative, what you're going to get the negative here, and you're going to get 3 times 5 times 7. You're going to multiply a bunch of odd things together here. 3 times 5 times 7 times 9. And the last one, let's see, we had 5 for the fourth derivative. Let's see, we had 3 for the second derivative. So it's probably like, because they're odds here, they're going up by 2 each time. So let's think about this as 3. Let's maybe think about the 3 times 2 would give me 6, but I'm 3 less than that. So it's like 2n minus 3 maybe. 4 times 2 would be 8, minus 3 is 5. So the last one, if I think this through, should be 2n minus 3 here, divided by 2 to some power here. Well, that power, let's see, is really just n here. And then I get a 1 minus x, and this 7 is sort of the first one that's missing. That's going to be to a negative 2n minus 1 over 2. Doesn't really matter what that exponent is, because I don't need this derivative necessarily to the power series. I need the derivative evaluated at 0, and my base is 1 here, so the exponent doesn't matter. So what we get is that the nth derivative evaluated at 0 looks like it's negative 3 times 5 times 7 times 9, multiply odd things together, times 2n minus 3 over 2 to the n. So now what we can do here is our Taylor series. You could write this here where it's summation n equals, well, it can't be 0 to infinity because this formula only works for n. Probably we need n to be at least 2 to make 2n minus 3 positive. So when you do n equals 0 here, we have a 1. So the first term is 1. 0 factorial is 1. X to the n is 1. So you get a 1. 1 factorial is 1. So you get a 1 minus 1 half over 1, which is still 1, minus 1 half x. So you'll get a 1 minus 1 half x, and then plus summation n equals 2 to infinity. You get a negative 3. So that negative inside, I'd probably write as a minus outside. 3 times 5 times 7 times 2n minus 3 over 2 to the n times x to the n. So this would be an okay answer here for our Taylor series. One thing where you can improve this is I have this dot, dot, dot here. So let's see if we can get a nicer formula for that. So 3 times 5 times 7 times 9 times dot, dot, dot times, 2n minus 3. So we're multiplying a bunch of odd sort of numbers together, a bunch of odd factors. Really, this looks kind of like a factorial, but the even terms are missing. So what I'm going to say here is this is really, I can throw 1 times out in front. Well, 1 doesn't change anything. This is 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9. And I just go up by 1, and then I'll get a 2n minus 2 and then a 2n minus 3. So I can keep this the same. I throw in all these even sort of factors that are missing from the factorial, but then I have to divide them out. So I have to divide by the 2, the 4, the 6, the 8, and the last one I divide out by is 2n minus 2. Okay, so that gets us there. And what we have on top then is really 2n minus 3 factorial over 2 times 4 times 6 times 8 times 2 times 2n minus 2. Now, on the bottom, everything's even. So you can rewrite this as 2 times 1. That's our 2. Our 4 is 2 times 2. Our 6 is 2 times 3. Our 8 is 2 times 4. And our 2n minus 2 is 2 times the quantity n minus 1. Here. So if you think of it that way, what you get is a 2n minus 3 factorial. Now, each of these factors in parentheses on the bottom has a 2. There's 1, 2, 3, 4, n minus 1 of them. So you factor out all those 2's, that's a 2 to the n minus 1. And what you're left with is 1 times 2 times 3 times 4 up to n minus 1. Well, that then is 2n minus 3 factorial over 2 to the n minus 1, and then we just have an n minus 1 factorial. So there we go with a sort of simpler formula here. So our Taylor series could be rewritten. Let's see if we've got enough space up above to write it. You can squeeze this in here. Well, no, let's just do it down here. So our Taylor series really could be written as we had the 1 minus the 1/2 x, that's minus x over 2, minus the sum n equals 2 to infinity, the formula we had above, which was this 1 times 3 times 5 times 7 times 9 to the 2n minus 3. Oh, I messed up my Taylor series before. Sorry. I did this formula for the nth derivative. There should have been an n factorial here. So there should have been an n factorial, which I left off. That comes from just the general formula for a Taylor series. It has an n factorial there, so I forgot that. Sorry. And then what I get is now this formula, 2n minus 3 factorial times 2 to the n minus 1 times n minus 1 factorial times n factorial times x to the n. So there's a sort of better formula for our Taylor series here for square root 1 minus x. Here, kind of a mess here, but it gets you an answer.